Okay guys, so like I said, calculus is the study of three topics. You don't need to write this down, I just kind of want to explain this to you, what we'll be doing. So calculus, the three topics we study, first of all are limits. Limits are used to find derivatives, so we have to understand limits before we can work with derivatives. The second topic is derivatives. So what a derivative does is it tells you the rate of change at any given point, and at one point. And that's what makes calculus so powerful, is because up to now, anytime you had a situation that could be modeled by a curve, you would have to know 2 points, and you could find the slope between those 2 points, and you could find the rate of change between those 2 points. Well, with calculus, we don't need to have 2 points to know the rate of change. So with calculus and the derivatives, I can find the rate of change at just 1 point. And that's what makes it so important. And it's used a lot in a lot of different areas because, like, let's say that this represents time and this represents our income. With calculus, if you have a model that connects your income based on the time, you can then instantaneously find the rate of change of your income compared to time. And so that's why it's so important, is that we don't have to have 2 points. By doing derivatives, we can find that rate of change at just 1 point. And that's what we'll be getting into after we finish limits. And then the other thing we study is called integration. And integration actually finds the area under any curve. So you know how to find the area of a rectangle, triangle, circle. Those are all shapes you can find the area under. But if I had a shape like this, something like that, and I asked you what's this area, it'd be pretty hard to find that area. But with calculus, if we know what the equation is for this curve, then with calculus we can find the integral, which looks like this integral symbol, and we can find the area of that region. Right? So again, we're starting with limits. Those will lead into derivatives. And then the last thing we'll do is this integration, which is this S symbol that we'll talk about much later in the year. All right, so now back to limits and what a definition of a limit is. So the limit of a function, if it exists, sometimes the limit does not exist. And we'll talk about when that happens. But the limit is simply the y value that the function gets closer and closer to as x gets closer to a specific c value from both the right and the left. All right, so that sounds a little confusing, but let me show you what I'm talking about here. So I can have some curve. Just maybe it looks like this. So I'm talking about one specific c value. So right here. If I want to find the limit right here, that means that as I approach this c value, the limit is simply what is the y value right there. So the y value might be 5. The y value might be 6. So the limit simply means the y value. As long as this function is continuous, the limit is just going to be f of c. So the limit equals f of c if the function is continuous. We're going to talk about all this a little more here in a minute, so you don't need to write any of this down. I just want you to listen. So if the function is continuous, that's going to be the case. The problem is sometimes we have functions that are not continuous. So we might have a function maybe like what you just had on your quiz, the secant curve. Okay, so the secant curve comes from the cosine curve. It's got an asymptote here, asymptote here, asymptote here. So here's what the secant curve looks like. So if I asked you for the limit as you approach pi over 2, can you see how the y value shoots way up as I approach pi over 2 from this side, and it goes way down as I approach pi over 2 from this side? So there's no specific value there that I can say. So for this problem, I would say the limit as x approaches pi over 2 of the secant curve, the answer to that is that it does not exist. DNE does not exist. Okay? So the only time we have to worry about this is if we're approaching something where the function's discontinuous. It's not continuous. Okay? Let's come back here now. So we're going to be doing some very simple ones to start with. So this example is read as the limit of x squared plus 2 as x approaches 3. So I'm going to think about this function, y equals x squared plus 2. What can you tell me about that function? It's a what? What kind of shape? Parabola that's been shifted up to. If it's inside parentheses, it's left and right. This is up to. So here's the way this parabola looks. You got a calculator there if you didn't know how it looks. So anyway, is this function continuous? Yeah, so I don't have any worries. All I have to do is plug in 3. So 3 squared is 9, 9 plus 2 is 11. That's all we're doing, is finding the y value. The limit is just a y value. So that's what we found right there. So many functions are continuous, meaning that there are no gaps or holes in the function. For these functions, we can simply plug in the x value c. So for continuous functions, the limit of f of x as x approaches c is simply going to be what? What did I just say you do? You plug in the c value. So it's going to be equal to f of c. So for these first problems we're doing, we're just going to think, are they continuous? If yes, then we know the answer is just meaning for the limit is just to plug in the value that we're given. Plug in that c value. In this case, my c value is 2. C just means x, guys. It just means a constant. So I plug it in. So I have 3 times 2. Oh, that's a negative 2. 3 times negative 2 plus 2. So negative 6 plus 2 is negative 4. Very straightforward. If you didn't know it, you could even use your calculator. Some of you don't use your calculator enough. Some of you use it too much. Most of you use it just right. But on a problem like this, it's not really necessary to use the calculator. But if I want to, I can look at my table. And all I have to do is say, when x is 2, what's y? Negative 4. I don't even have to do anything. All right, 2 now. Number 2. We're finding the limit of this as x approaches negative 1. This is our same function we just did a second ago. Very similar to it. This will be a shift up 4. It's a parabola. It's continuous. All we do is plug in negative 1. What do we get, everybody?
5.
5 is right. The next one, the sine of x over 6. This is just a sine curve where the period has changed. Is the sine curve continuous? Yeah. So all I have to do is plug in my value. It's a continuous function, so I just plug in the sine, plug in pi for x of pi over 6. Do you know the sine of pi over 6? Some people do, some don't. Pi is 180. 180 divided by 6 is 30. If you need to, draw a picture. Across from the 30s, 1, radical 3, 2, 1/2. I want you to be able to do that more quickly, but I was just showing for people who don't remember that. All right, for this one, the limit as x approaches 0 of cosine x. Well, cosine x is a continuous curve, so I just plug in 0. The cosine of 0. You guys know it? 1. Some people are saying 1. It is 1. Here's the reason why. Think of the unit circle. Right here's the point 1, 0. Cosine is always the x value. So my x value is 1. So that's going to be our answer. What about the tangent curve? Is tangent continuous? It's not. But is it continuous at 2 pi over 3? Maybe you're not sure. Well, here's the way the tangent curve looks. It has asymptotes at negative pi over 2, pi over 2, 3 pi over 2. This is why we learned about this earlier in the year. So here's the way the tangent curve looks. So 2 pi over 3 is right about here. It's continuous right there, isn't it? So that means I can evaluate it. So I'm just trying to do the tangent of 2 pi over 3. Pi is 180 divided by 3 is 60 times 2 is 120. So I'm looking at 120 degrees. Pi over 3, 60, that's my reference. This is radical 3, this is 1, this is negative. That's 2, I don't even need it. And I do opposite over adjacent. And so what's this answer going to be? Right. If you use a unit circle, great. Go ahead and use that if you haven't memorized well enough. All right, the limit of cotangent x. Do you remember what cotangent looks like, where its asymptotes are? Anybody know where the first one is? I gave you a little hint. The first one is at 0. 0. So cotangent looks like this. It's got an asymptote at 0, asymptote at pi, asymptote at negative pi, and it always goes down too. Down. And it's got an asymptote at 0. See, the tangent has its asymptotes at negative pi over 2, pi over 2, 3 pi over 2. But this one's at 0, pi, negative pi, etc. So at 0, can I find a limit at x equals 0? No. Because this is from the left, it's going way down. From the right, it's going way up. So we say the limit does not exist. Any of you see that movie, Mean Girls, where at the end she's like, the limit does not exist? Yeah. All right. So if you're not sure, might be a good option just to say the limit does not exist. Sometimes it works for you. But only if you have a discontinuity there.
You like movies?
Yeah, good movie. Good. I don't like them in real life, but I liked the movie. Okay. The limit of a composite function. If f and g are continuous functions such that the limit as x approaches c of g of x equals L, and the limit as x approaches c of f of x equals L, then we can find the limit of a composite function f of g of x by doing this. This is the bad thing about calculus, is that the notation looks so difficult, okay? You know, you're in a college class and the professor throws this up and says, yeah, just do this and you've got it. Like, what are you talking about? But the nice thing about calculus is it's very intuitive. Whatever you think you should do, if you do that, it's going to be right. Let me explain what I mean by that. So they're telling us all this crazy notation here. But all it's saying is to do what we've been doing with the composite functions. So we're going to plug c into g of x and then plug that value into f of x. That's what we've been doing. So this limit looks a little confusing because it's a composite function. We're given f of x as x plus 7. We're given g of x as x squared, and we're supposed to find these. Well, to find the limit of f of x as x approaches 3, I plug it in. What do we get? 10. Okay. Now I'm supposed to do this. The limit as x approaches 3 of g of f of x. Well, really, guys, all you have to do is this problem. It's exactly what you would think it would be. We just did that on our quiz. So we plug our 3 into our f function. We get 10. And then we take our 10 and we plug it into the g function. So we're doing g of 10. So 10 squared is 100. Okay, questions there? So what are we going to do on this one? Plug 3 in where first? G. Plug in 3 to G. What do you get? 9. So then we plug that into F, and what do you get? 16. Okay, so it looks complicated, but it's not. All right, I want you guys to do the next 3 on your own. Okay, just from using what we had in the previous ones. So there's what our functions were. So go ahead and do those pretty quickly. So remember, on this one, you're going to plug 2. Which do you plug 2 into first, F or G? F. Plug 2 into F, get that answer, and then plug that answer in for G. All right, Allie, what'd you get for the first one?
25.
Everybody agree? Okay. Nick, what'd you get for the second one? 11. Do we agree? Good. So on this one, what we're doing, we're plugging 2 into our g function. 2 squared is 4. 4 plus 7 is 11. Okay, and then the last one, we're going to plug 0 into our f function. What do we get? We get 7 for that. And then we're going to plug 7 into our g function, and we get 49. All right, guys. Last thing here, this is a review on graphing piecewise functions. You've done this before in pre-calc, but it's something that's important for calculus to be able to do see whether it's continuous or not. So what I'm going to have to do is I'm going to have to graph y equals x squared, but only for x's that are less than or equal to 3. Then I have to graph y equals x plus 1, but only for x's that are greater than 3. A lot of people like to make an XY chart. So that's what I'm going to do. 3 is the breaking point. So I'm actually going to put 3 into both of these functions. If I put 3 into the first function, 3 squared is 9. That's going to be a closed dot. If I put 3 into the second function, I get 4. That's going to be an open dot. A lot of people say, well, why are you putting 3 into the second one? Because 3 is not greater than 3. Well, what about 3.01? Is that greater than 3? Yeah, and I don't really want to have to check 3.01 and 3.02 and 3.03. So what I do is I just check this and I use an open dot. So, yeah.
How do you know if it's closed or open?
Because if it's equal to, it's going to be closed. And if it's just greater than, it's going to be open. All right, so now I'm going to check some other numbers. I'll check like, I don't know, 2, 1, 0. So all of these x values are less than 3, so they're going to get plugged into my top function. 2 squared is 4, 1 squared is 1, 0 squared is 0. Any number I choose for x that's greater than 3 gets plugged into the second one. 4 plus 1 is 5, 5 plus 1 is 6. So now I'm going to start plotting these points. 0, 0, 1, 1, 2, 4, and then 3, 9. Okay, now stop right here and think before you go on. Here's where people get confused. They just connect these dots and they think they're finished. No, we are graphing this anytime x is less than or equal to 3. So this has to go on forever down this way. What kind of shape am I graphing if it's y equals x squared? A parabola. So it's going to be a parabola that has had no shift. So it should look like that. Even though none of these points show me that, I just have to know that. For my other part, I know I have the point 3, 4, and I'm going to have an open dot. I've got 4, 5, etc. So here's the way it's going to look. Now, maybe you're not sure about that. Well, let me remind you of how we can check it on the calculator. Go to y equals. We're going to do y equals x squared. But I have to say divide it up. It's not like I'm truly dividing. It's that I'm dividing up the function. So I'm dividing it up so that x, do you remember where less than is located? Under test, so second math, and I need it to be less than or equal to 3. And then I come down to y sub 2, and I put in x plus 1. Divide it up, though. Only graph this when x is greater than 3. Some things you want to watch for. Go up here to the top. Make sure your plots are off. If you have this highlighted, your plots are on. And it's going to look weird, and you're going to be like, what's wrong with my graph? Well, it's because your plots are on. Turn it off. Okay? The other thing is you want to do a zoom 6 to get to your standard screen. Here's the way it says it should look, and that's what we've got. The calculator can't show us the closed and open dots. It doesn't it's not that, I don't know, technologically advanced, I guess we'd say. push trace. Look here, guys. See how it stays on this function for all of these x's? And then all of a sudden it says, well, there's nothing there. Notice that happens when I get past 3. Look at what function it's on. It's on the first function. It's saying on the first function, there's nothing there for y. But look if I arrow down and I say, well, use the second function. See how now when x is greater than 3, it shows me values for y? So it's saying you got to use the second function anytime x is greater than 3. Okay, so that's a good thing too. Another cool thing is I can look at my table now, and it's showing me for all of these x's you're using y1. For all of these x's you're using y2. So that even helps me just to know, how to evaluate anything that I were to ask you now about the function. All right, last thing, I want to see if you guys can do this. Write any limit problem with correct notation, and I want your answer to be 8. Okay, any limit problem. Look, you can look back over here. Look at how they're written. You can make it as complicated or simple as you'd like, but make your answer be 8. Well, however you want to write it. You can write it like we did at the beginning. You can write it with the composite functions. You might have one. AJ, bring yours up. All right, we're going to look at his, see if we agree. All right, yeah, this works, doesn't it? He's got correct notation. The limit of x plus 8, that's a continuous function. He needed continuous. Plug in 0, you get 8. Perfect. Thank you. Okay, lots of different options there. Any questions on beginning limits? All right.